Have you ever just stopped and thought about the invisible forces that are quite literally powering everything around us? You know, from the phone in your pocket to the lights across your entire city, it all runs on a secret set of rules. Today, we're going to pull back the curtain on those rules. We're diving into circuits and electromagnetism to really understand the magic behind the tech we use every single day.
I mean, it sounds a little crazy, right? How can a spinning magnet and a bit of wire possibly generate enough juice to power millions of homes? It feels like it should be more complicated than that. Well, that's the big question we're going to tackle. And trust me, by the time we're done here, you'll get exactly how it all works.
So, here's our game plan. We're going to take this in 4 steps. First, we have to learn the basic language of electric current. Then we'll venture into the kind of mysterious world of magnetism. After that, and this is the fun part, we'll see what happens when these two forces team up. And finally, we'll see how that powerhouse combination is the backbone of our modern world.
Okay, before we can get to all the mind-blowing stuff, we've got to start with the basics. You can think of this first part as learning the ABCs of electricity. We need to get the fundamentals down first. You know, pretty much every circuit you can imagine is built using 2 basic layouts, series and parallel. A series circuit is like a one-lane country road. All the traffic, or current, has to flow through every single component, one after the other. No other choice. But a parallel circuit, that's more like a highway with multiple lanes. The current gets to a split and it divides, taking different paths. And as you can see from the math, that simple difference completely changes how you figure out the total resistance of the circuit. So to keep all this electrical traffic from getting chaotic, there are 2 unbreakable laws of the road. We call them Kirchhoff's rules. The junction rule is super simple. What goes in must come out. At any intersection in a circuit, the amount of current flowing in has to equal the amount flowing out. Charge can't just vanish into thin air. Then there's the loop rule. This one says that if you make any complete round trip in a circuit, all the energy boosts you get from a battery have to be used up by everything else. It all has to zero out. Perfectly balanced. Now, if we want to actually measure what's going on, we need the right tools, and we have to use them the right way. To measure voltage, you grab a voltmeter, and you connect it in parallel, meaning you tap into 2 different points to see the difference between them. It needs a crazy high resistance so it doesn't siphon off any of the current for itself. But to measure current, you use an ammeter. And for this, you actually have to break the circuit open and stick the meter in series, so all the current has to flow through it. And for that to work, it needs almost 0 resistance. See? They're total opposites by design. Okay, so we've got a handle on how charges flow. But what happens when they actually move? Well, something pretty incredible. They create a whole new type of force field out of thin air. And this is our gateway from simple electricity into the amazing world of magnetism. Yep, every single moving charge, every one, from the electrons in a tiny wire to a particle zipping through deep space, generates this invisible field of influence all around it. We call this the magnetic field, and we use the letter B to represent it. It's the exact same force that pulls a compass needle north, and we measure how strong it is in a unit called the Tesla, named after the legend himself, Nikola Tesla. So how in the world do you figure out which way this invisible force is going to push a charge? Well, physicists came up with this awesome little trick called the right-hand rule. Seriously, try it with me. Just take your right hand, point your fingers in the direction the charge is moving. Now point your thumb in the direction of the magnetic field. The direction your palm is facing, that's the direction of the force. It's like a built-in cheat code for visualizing these forces. Okay, so a single charge gets a little push from a magnetic field. Big deal, right? But what happens when you have trillions upon trillions of charges all flowing together inside a wire as a current? Well, they all get pushed together, and that tiny little push on each one adds up to a real, tangible force on the wire itself. This idea, summed up in that equation, is the secret behind every single electric motor on the planet.
And this leads to a really important point. It's not just your typical refrigerator magnets that make these fields. Any electric current creates a magnetic field. And what's really cool is that the shape of the wire, whether it's just a long straight wire or a neat little loop or a tightly wound coil called a solenoid, that shape determines the exact pattern and strength of the magnetic field it produces.
All right, deep breath. This is where it all comes together. We've talked about electricity and we've talked about magnetism as 2 separate things. Now, we're going to see what happens when they start to interact. This is where the real magic happens. So, to get the magic trick, we first need to understand something called magnetic flux. Imagine you're holding a hoop out in a rainstorm. The flux is just how much rain is passing through your hoop. It's the same idea with magnetism. Magnetic flux is just a way of counting how much of that magnetic field is actually passing through a certain area, like a loop of wire.
So you have a magnet just sitting there next to a wire. Nothing happens. Kind of boring. But what if you start to change things? What if you move the magnet closer, or pull it away, or maybe spin it around? What happens when you change the amount of that magnetic flux that's going through the loop?
And here it is. This is the answer. This is one of the most profound and important discoveries in all of physics, Faraday's law of induction. It says that if you simply change the magnetic flux going through a loop of wire, you will literally create a voltage out of nowhere. You induce it. That's the whole secret. Moving a magnet near a wire creates electricity. This one idea is how we generate virtually all the power on Earth.
But what about that little minus sign in the equation? It's not just for looks. That's where Lenz's law comes into play. It's basically nature's way of pushing back. It says that the current you create will immediately generate its own magnetic field that fights against the very change that created it. So if you try to push a magnet in, the wire will create a magnetic field to push you back out. It's nature's way of making sure you can't get free energy.
So we've cracked the code. We know the secret. Now let's look at how we've used this incredible principle to build our entire global power system using something called alternating current, or AC, circuits. Now, in AC circuits, the current is constantly flipping back and forth, and that introduces a couple of new ways a circuit can fight back, besides just plain old resistance. Inductors, which are just coils of wire, they hate change. They fight against fast-changing currents. We call their opposition inductive reactance. Capacitors are the exact opposite. They block steady currents, but let fast-changing ones pass right through. We call that capacitive reactance. And as you can see, the faster the current changes, the higher the frequency, the more the inductor fights it, and the less the capacitor does. They're perfect rivals. So to get the total opposition in an AC circuit, you can't just add things up. You've got resistance, and you've got these two opposite forces of reactance all fighting the current at the same time. So we combine all three using this formula here to get one final number called impedance, which we represent with a Z. This is the ultimate, all-encompassing measure of opposition in an AC circuit. And this whole rivalry leads to a really amazing effect called resonance. You see, there's a special frequency, a sweet spot, where the inductor's opposition and the capacitor's opposition are exactly equal, so they completely cancel each other out. At that one perfect frequency, the total impedance of the circuit drops to its absolute minimum, and that lets a huge amount of current flow. This isn't just a party trick, it's exactly how you tune a radio. You're adjusting the circuit to find the resonant frequency of the station you want to hear.
And finally, we get to the transformer. This is the ultimate application of Faraday's law. It's just two coils of wire near each other, and it lets us change AC voltages with incredible efficiency. The rules are simple. If your second coil has more turns of wire than the first, the voltage goes up. We call that a step-up transformer. If it has fewer turns, the voltage goes down. That's a step-down transformer. Without these amazing devices, our power grid would be impossible. They are the unsung heroes of our electrical world. So there you have it. We started with a pretty simple question about a wire and a magnet, and we ended up with the blueprint for our entire technological society. We saw how moving charges create magnetism and how changing magnetism creates moving charges. It's this beautiful, powerful dance between two forces, and it really makes you want